Right now, the sun is burning. It has been burning for 4.6 billion years. And for most of that time, nothing on Earth has had any reason to worry about it. It rises, it sets, it warms the oceans, drives the winds, feeds every living thing on this planet. It is so reliable, so constant, that humanity has built entire religions around it, entire calendars, entire civilizations. But the sun is not eternal. It is a star, and like every star in the universe, it has a death waiting for it. A death so enormous, so total, that the word catastrophe doesn't come close to describing it. The word extinction doesn't either. What happens when the sun dies isn't just the end of life on Earth. It's the end of Earth itself. This is the story of that death, told not in abstract numbers, but in moments. In the final chapters of a story that started before our planet even existed. And it begins not with an explosion, not with a warning. It begins with light.
The day the sun dies.
5 billion years from now, the sun begins to change. The first sign is almost invisible. To any observer standing on a distant world, our sun would look more or less the same. A yellow-white star, medium-sized, unremarkable by cosmic standards. But deep inside its core, something has been quietly shifting for hundreds of millions of years. The hydrogen that has fueled the sun since its birth is running out. For 4.6 billion years, the sun has survived through a process called nuclear fusion. Every second, 600 million tons of hydrogen are converted into helium inside its core. The energy released by that process is what we see as sunlight, what we feel as warmth, what makes photosynthesis possible, what keeps liquid water on our planet, what makes life not just possible but inevitable. But hydrogen is finite, even in a star. As the core hydrogen depletes, the sun compensates. It begins to burn the hydrogen in the layers surrounding the core instead. This is a subtle change at first, barely perceptible, but it has consequences. The outer layers of the sun start to expand. Slowly, incrementally, over millions of years, the sun grows larger. And as it does, it grows brighter. On Earth, if Earth still exists in its current form, if anything recognizable still walks its surface, the change would be gradual enough that no single generation would notice it. The days would grow marginally warmer. The polar ice caps, already stressed, would begin a retreat that would not stop. The oceans would warm. Weather patterns that took billions of years to stabilize would begin to shift again. This process has actually already started. The sun today is about 30% brighter than it was when life first emerged on Earth. In another billion years, it will be bright enough that liquid water on the surface of Earth becomes increasingly difficult to sustain. In 2 billion years, the surface of our planet may more closely resemble Venus than the world we know today. But this is only the beginning, the slow burn before the real transformation. The red giant phase, approximately 5 billion years from now. There is a moment, not a sudden moment, but a geological one, stretched over tens of millions of years, when the sun crosses a threshold. The core, now dense with helium ash, contracts under its own gravity. The temperature rises sharply, and the outer layers of the sun, responding to the increased energy output, begin to expand in earnest. Not by a small amount, not by a factor of 2 or 3. The sun swells outward by a factor of roughly 200. What was once a sphere 1.4 million kilometers in diameter becomes a bloated, reddish giant more than 200 million kilometers across. This is what astronomers call a red giant. To understand what this means for the inner solar system, consider the current distance from the Earth to the Sun. That distance is approximately 150 million kilometers. It takes light 8 minutes to cross it. A passenger jet traveling at cruising speed would take 17 years to cover the same ground. The expanded Sun would engulf everything within roughly that distance. Mercury, the closest planet, would cease to exist, vaporized, absorbed into the outer atmosphere of a star that has grown large enough to swallow it whole. Venus would follow, a world already hellish by any human standard, surface temperatures hot enough to melt lead, atmospheric pressure 90 times that of Earth, would simply disappear into the expanding plasma. And then comes Earth. The models here are not entirely settled. Some calculations suggest that Earth, pushed outward slightly by the reduced gravitational pull of a sun that has lost mass through stellar winds, might just barely survive the initial expansion. Others suggest it will be swallowed. Either way, the outcome for anything on the surface is the same. Long before the sun's outer atmosphere reaches Earth's orbit, the planet will have been stripped of everything. Its oceans will have boiled away billions of years earlier. Its atmosphere will have been blasted into space by the intensified solar wind. Its surface will be a scorched, airless rock orbiting in the outer envelope of a dying star. If there are still satellites in orbit at that point, ancient machines launched by a civilization that no longer exists, they will be among the last artifacts of everything humanity ever built. Drifting, darkening, finally consumed. What happens to the outer planets? What happens to the outer, while the inner solar system is being remade by fire? The outer planets will experience something almost stranger, something harder to fully picture. Jupiter, Saturn, Uranus, Neptune, the gas giants. Worlds so large that all the rocky planets combined could fit inside them without filling the space. These planets currently exist in the cold outer reaches of the solar system, separated from the sun by distances that make the Earth-Sun gap seem trivial. Jupiter orbits at 778 million kilometers from the sun. Neptune at nearly 4.5 billion. The expanding sun will not reach them. Not directly, but it will change them. The increased luminosity of the red giant sun will push the so-called habitable zone, the band of distance from a star where liquid water can exist on a planetary surface, dramatically outward. Worlds that were once frozen will warm. Europa, one of Jupiter's moons, currently has a liquid ocean beneath a thick shell of ice. In the red giant phase, that ice shell would begin to melt. Enceladus, orbiting Saturn, with its geysers of water vapor erupting from beneath its frozen crust, would be transformed. For a period measured in hundreds of millions of years, the moons of the outer solar system might experience something resembling temperate conditions. Whether life could emerge in such a compressed window of time is a question science cannot yet answer. But the universe has a long history of surprising us. Saturn's rings, one of the most beautiful structures in the solar system. A disk of ice and rock so thin relative to its diameter that if scaled to the size of a sheet of paper, it would be thinner than that paper, would likely begin to evaporate. The ice would sublimate. The rings would fade. The most iconic silhouette in the solar system would dissolve over millions of years into nothing. The helium flash, a moment 5 billion years away that will last 2 seconds. Inside the core of the red giant sun, something has been building for millions of years. The helium ash that accumulated from billions of years of hydrogen fusion has been slowly compressing, getting denser, getting hotter, until it reaches a temperature of approximately 100 million degrees Celsius. At that point, helium begins to fuse. The energy release is almost incomprehensible. In the space of a few seconds, the sun's core releases as much energy as the entire Milky Way galaxy produces in a week. This event is called the helium flash. It happens in an instant by stellar standards, and it is invisible from outside the star. The energy is absorbed by the outer layers before it can escape. From a distance, nothing appears to change, but inside, everything has changed. The core stabilizes. The sun's outer layers contract slightly. For a period, the sun enters a new phase of relative stability, fusing helium in its core the way it once fused hydrogen. This phase is shorter, much shorter, perhaps 100 million years compared to the 10 billion years of hydrogen burning. Then the helium runs out too. The Planetary Nebula, the sun's final gift to the galaxy. When the helium in the core is exhausted, the sun enters its final active phase. The core contracts again. The outer layers expand again. But this time, there is no new fuel waiting to ignite. The outer layers, thin and diffuse by this point, begin to drift away entirely. Pushed outward by the stellar wind, They expand into space as a slowly growing shell of glowing gas. This is what astronomers call a planetary nebula, a name that is actually a historical accident, coined by early observers who thought these glowing clouds resembled planets through their telescopes. They have nothing to do with planets. What they actually are is the outer layers of a dying star, dispersed, illuminated by the ultraviolet radiation of the exposed core, expanding at speeds of tens of kilometers per second. Over tens of thousands of years, this shell will grow to encompass a volume of space larger than any structure in our solar system, larger than the entire orbit of Neptune. From a distant star system, our sun in this phase would look like one of the most beautiful objects in the sky. A glowing ring of blue and red and violet. A cosmic halo, the kind of structure that fills astronomy textbooks and graces the covers of science magazines. It would also be the grave marker of everything that ever lived here. Inside that expanding shell, all that remains of the sun itself will be the core. A dense, Earth-sized object composed almost entirely of carbon and oxygen. No longer fusing, no longer generating energy through nuclear reactions, just radiating the heat it has stored, slowly, over billions and billions of years. This is what astronomers call a white dwarf. The white dwarf, the long silence. A white dwarf is not a star in any meaningful sense. It is a remnant. Okulingember. Our sun's white dwarf would begin its existence at a surface temperature of roughly 100,000 degrees Celsius. Hotter than almost anything in the solar system today. But without a fuel source, it can only cool. And it will cool. Over hundreds of billions of years. A timescale so long that the current age of the universe is barely a footnote within it. The white dwarf will slowly fade. From white to yellow. From yellow to orange. From orange to red. From red to a dim infrared glow that no human eye could detect. Eventually, in theory, it will become what physicists call a black dwarf. A cold, dark, inert sphere of crystallized carbon and oxygen drifting silently through space. Invisible, detectable only by the faint gravitational pull it would exert on anything passing nearby. The universe, however, may not be old enough for any black dwarfs to exist yet. The estimated time required for a white dwarf to cool to black dwarf temperatures is longer than the current age of the universe. By many orders of magnitude, the oldest white dwarfs we can observe today are still glowing, still warm, formed from stars that died in the earliest chapters of the galaxy's history, which means every black dwarf that will ever exist is still a white dwarf right now. Our sun will join that list. It will cool for longer than anything in human history, human prehistory, or the entire fossil record has any frame of reference for. And at some point, so far in the future that the number of years required to describe it would fill the script several times over, it will go dark. What remains? In the region of space where the solar system once existed, there would still be objects. Ghosts of the original architecture. Jupiter and Saturn, though altered by billions of years of exposure to a dying star, would likely survive the sun's expansion. Their cores, dense, massive, composed of materials that do not easily evaporate, would persist. Stripped of their gas envelopes over millions of years, they might end up as dense super-Earths. Rocky worlds, silent, cold, orbiting a white dwarf at enormous distances. The outer reaches of the solar system, the Kuiper belt, the Oort cloud, the vast reservoir of comets and icy bodies that extends nearly a quarter of the way to the nearest star, would be scattered by the gravitational disruptions of a sun that has shed a significant portion of its mass. Some objects would drift inward toward the white dwarf. Others would be ejected entirely, sent on trajectories that would carry them out of the solar system altogether and into the interstellar void. The white dwarf itself would occasionally be visited by these fragments. Comets and asteroids, perturbed from their orbits, would fall inward and be torn apart by tidal forces. Their material would form a disk of debris around the cooling remnant. Spectroscopic observations of white dwarfs in our galaxy today already show this exact pattern. Heavy elements, silicon, iron, calcium, in the atmospheres of white dwarfs that should by all rights contain only hydrogen and helium. Contamination from the ruins of planetary systems that the white dwarf has consumed. We have already observed the aftermath of other stars dying. The evidence is written in light that left its source millions of years ago and has only just reached our telescopes. And somewhere, around one of those distant white dwarfs, there may be the crystallized remnants of worlds that once had oceans, atmospheres, weather, maybe more. The perspective. Here is what makes this story different from a simple catastrophe. The sun is not malfunctioning. It is not broken. It is not doing anything wrong. It is doing exactly what a star of its mass is supposed to do over the course of its natural lifetime. The hydrogen it was born with is finite. The physics that govern its behavior are the same physics that govern every star in every galaxy in the observable universe. There is no version of stellar evolution in which a star like the sun does not eventually become a red giant, shed its outer layers, and leave behind a white dwarf. This is simply what stars are. And Earth, everything that has ever lived on it, everything that has ever been built on it, every ocean and mountain and city and fossil, exists inside a window. A window that opened roughly 4 billion years ago when the first self-replicating molecules appeared in warm, shallow water. A window that, by cosmic standards, is extraordinarily narrow. And a window that will eventually close. Not because of anything life does or doesn't do, but because the physics of the sun demands it. The dinosaurs ruled the Earth for 160 million years and never knew any of this. The first humans appeared roughly 300,000 years ago. Agriculture, writing, cities, science, all of it fits inside the last 10,000 years. A fraction of a fraction of a fraction of the time that complex life has existed here. We are extraordinarily early in the story of this planet. And yet we are the first species, as far as we know, to have looked up at the sun and understood what it is. To have calculated its remaining fuel reserves. To have modeled its future. To have written down what will happen to it 5 billion years from now. That is either the most remarkable thing about us, or the most humbling. Possibly both. The sun will rise tomorrow, and the day after, and for billions of days after that. Long after anything living today has turned to dust and carbon and memory. But one day, in a future so distant it has no name, it will not rise. And the universe will continue. The universe is vast, mysterious, and we've only just scratched the surface. If this journey sparked your curiosity, hit like, subscribe, and share it with someone who loves to wonder. Every bit of your support helps us dive deeper into the unknown. We'll see you on the next adventure.